Hey, this is Horner, and this one is 1997 M2. So, a little bit older question, but still a good question. This one, we have an open top railroad car. Initially, it is empty, and it has a mass of M0. It rolls with negligible friction. And so, when you do these, I would probably do something like for this one, put M0 in it and then write no force of friction, exclamation point. So that way you know you're not losing any energy along a straight horizontal track and passes under a spout of a sand conveyor. So we know that there's sand coming out here. When the car is under the conveyor, the sand is dispensed from the conveyor in a narrow stream at a rate. So here is a rate. So this is the change in mass over the change in time. So it's kind of like a velocity, but you can think more of a velocity in terms of the sand coming out. And they give that a value c. So that's kind of like when we say velocity, whoops, I know I put x and I didn't really mean to, so we'll get rid of the x. So that's where velocity is change in position over change in time. Here we're just saying that this flow rate c is equal to the change in the mass of that sand over the change in time. The car has an initial speed of VO, so we're going to put VO is the initial speed of the car, and the sand is filling it from time 0 to time equals t. Express your answer in the following following to the following in terms of the given quantities and g, which is the acceleration due to gravity. All right, here we go. Determine the mass m of the car plus the sand that it catches as a function of time. For 0 is less than t, which is less than capital T, which is that entire time. So to do that, we're going to say that big M is that total mass, and that's equal to MO, which is the original mass of the cart, plus, and then we need to do that flow rate. Remember, the flow rate is delta M over delta T, so that's the amount of sand that's coming through, times the time. And so all we have to do here is just say M is equal to MO plus substitute in C for this, and that is C times time. You get 2 points for doing that. You get 1 point for this, and then you get 1 point for recognizing that delta M over delta T is C because that is what they told you. Next part says determine the speed v of the car as a function of time. For 0 is less than t, which is less than capital T. So we know that the original mass times that original velocity of the car is equal to the final mass of the entire thing times the final velocity of the entire thing. So we need to go ahead and say MO, VO, that doesn't change, is equal to, now we need to substitute in the expression for the total mass from part A. So the total mass, and really I would put a T there because that's the total mass times velocity, but that's just me. So this is the original mass of the cart plus that C times T that we did above, and then that is times that final velocity. So let's go put an F right there too. Now that we've done that, we can solve for that velocity. So our velocity here is equal to, final velocity is equal to our original mass times original velocity, all divided by the mass original plus CT times the nothing, right? Because we already have the VF there. So once again, we have conservation of momentum, and then you need to do everything to have this kind of come out and go through. So that should be really easy to do. Next part of this one is looking at letter C. And here it wants us to determine the initial kinetic energy, Ki, of that empty car. So to find the original kinetic energy of the empty car, we know that kinetic energy, Ki, is equal to the original mass of the car times the original velocity of the car. But here, we have to divide it by 2 because remember it's 1/2 mv squared. So instead of doing the half, we're just going to divide by 2. So you get a point for doing that. Super, super simple. For part 2, this one that says determine the final kinetic energy, Kf, of the car and its load. So they've really broken this one down to try to get everything together. So here's our original, we're going to do our final, and then they're going to ask us if it is conserved and then ask us why or why not. So this is equal to 1/2 of the total mass times velocity squared. And we have to remember what we were using earlier, and we said that Kf is equal to, so now we're going to use that original mass plus the modified mass. We're going to divide that by 2. So this is the total mass divided by 2. And then we've got to put in MOVO over MO plus CT. And remember that is our velocity, and so that's squared. And now you are done. If you wanted to, you could simplify this, and if you simplify it, I'll just move this up here. Final kinetic energy is equal to MOVO, and these are both squared. So there's that MOVO squared, and then we're going to take that over 2 times MO plus C times T. So if you square the top, you get this. If you square the bottom, then you can cross one of these off with one of those down here, and then we're just going to kind of put a dotted line through, kind of like this, just to show that we're only going to get rid of one of those, so that's 2 times this, and that's how you go through and do that. So the question is energy conserved? And we know that in an inelastic collision, it is not conserved. Not conserved. They want to explain why not. In elastic collisions, lose energy to, and we're going to call these dissipative. So they lose it to dissipative force, dissipative energy, like heat and sound. And if you think about it, if you have 2 metal balls and they roll towards each other, when they hit, you hear that loud clack. So that loud clack is energy that's being given off in the form of those new sound waves that you've determined, that you've made. Next thing they want us to do here is determine expressions, so notice that's plural, for the normal force exerted on the car by the tracks at the following times. So we're going to do that for each one of these. So at the very beginning, we know that we have straight down, we've got mg, and straight up for the car, we've got the normal force. So this one's really easy. We just know that N is equal to the mass of the car, which we said was MO, times G. For this one at time, so we've got from 0 less than T, which is less than capital T. The normal force here should be equal to the car plus the weight of the sand that's accumulated in the car plus the force required to stop the vertical motion of the sand. So there's a lot there. So the normal force here is equal to the mass of the car, which we said was MOG, plus the weight of the sand, so that is MS times G, plus that force that is required to stop the vertical motion of the sand. So we're just going to call that Fs. And the correct expression for the weight of the sand is not going to be MSG. Because remember, we don't really know what MS is, but we do know that this is C times T times G. and that gives us the weight of the sand. So CT was mass, and then gravity is G. So now we've got to calculate Fs in terms of the sand's change in momentum. So in order to get Fs, we're going to say Fs is equal to the change in momentum over the change in time. That is equal to the change in the mass over the change in time times the velocity in the y. And so that's just equal to, remember we said m over t is c, and then we multiply that times velocity in the y direction. To find Vy now, we can apply kinematic equations or the conservation of energy for the filling sand. So we know that 1/2 m times Vy squared is equal to mgh. So the m's cross off, and now we're left with Vy is equal to the square root of 2 times g times h. So now we can plug everything back into our equation. So now we've got N is equal to MOG plus CTG, and then we can add to that plus, and then remember C, times Vy, but we said Vy is equal to the square root of 2GH. If you want to simplify this, you can factor out a G, and we can make it N is equal to MO plus CT, and then we're going to take that and multiply it times G plus C square root of 2GH. And so that is that part. The very last part, it says after T is equal to the time. So we know that now we've got all the sand is accumulated on the inside, so the normal force here is just going to be equal to the cart or the car plus the sand. So let's do that. N is equal to, and we've got the mass of the car plus the mass of the sand, which we said was CT, and then we're going to multiply that times gravity. So a really weird problem, but a really good one to get you kind of going through and thinking about all these things. So this is a pretty nice problem to be able to go through and know how to do.